The full thermochemical state describing a burning flame is highly dimensional. For constant pressure systems, a flame can be described with temperature and mass fractions of all but one chemical species present in the chemical mechanism. Therefore, simulating combustion problems numerically requires solving equations for many parameters. But can we simplify this description by choosing some optimal set of many less parameters? For non-parametric systems, one such good candidate for a compressed parameter is mixture fraction, which only looks at the local stoichiometry of the flame, but does not look at any other effects, such as heat transfer, for example. Therefore, this parameter is usually necessary, but not enough, because for a single value of mixture fraction, the flame can be in vastly different state of reaction. The stoichiometry alone cannot successfully differentiate between those reacting states. But if we crafted one extra parameter that now spans the reaction progress dimension, these two parameters combined could already be enough for many combustion problems. The question is, how do we define this reaction progress variable so that the complete parameterization is successful in numerical simulation? This is the topic of our latest paper published in Combustion and Flame. In the past, researchers have defined those reaction progress variables, or PVs, manually, using some intuition behind which definition might work well. And in this work, we show that the two ad hoc definitions used in the ammonia combustion literature can exhibit some problems. For example, this definition, which is simply the mass fraction of NO species, doesn't work for this particular combustion dataset because it leads to non-unique parameterization in the 2D space spanned by mixture fraction and PV. Such non-uniqueness can have detrimental effect in a numerical simulation. The second example definition, which takes mass fractions of these three species, is also not so great, as it leads to high compression of this combustion dataset, steepening the gradients in various variables, which can also pose a modeling challenge. In this work, we show a strategy to optimize definitions of progress variables so that the behaviors such as non-uniqueness or steep gradients are minimized or do not occur at all. But even more than that, our strategy allows to alter the shape or the topology of this parameterization such that important quantities of interest are represented as best as possible. This gives the modeling community a chance to adapt parameterization topologies towards variables that are of most interest at a given time. We may, for example, be particularly interested in modeling pollutant formation, for example, NOx species. We also inject as one of the important quantities of interest the source term for the progress variable, which shows up in the transport equation for the PV. And during numerical simulation, it will be crucial to predict the source term well, and therefore our optimization of a PV should also simultaneously optimize its source term. And to accomplish this, we train an encoding-decoding neural network with a specialized architecture. We connect a linear encoder, which computes the optimized PV, with a nonlinear decoder, which reconstructs important quantities of interest from the parameterization. At the input to the neural network, we pass all chemical species mass fractions, and hence we allow the PV definition to be a linear combination of any of the species mass fractions, where the weights of that linear combination get optimized through gradient descent. We also force the second parameter to be mixture fraction, and this is done by adding a non-trainable connection that just passes through the mixture fraction. And eventually our parameterization is two-dimensional, composed of a PV and a mixture fraction. At the decoder output, we reconstruct important quantities of interest, And there, the user has freedom to include any QOIs whose predictions from a numerical simulation are important. We also add the source term of the PV, which is a linear combination of the chemical source terms of all the species, with the weights being the same as the ones defining the PV. So note that the definition of the PV source term continually changes during training as those weights are changing. And we find that we obtain very good quality parameterizations with mixture fraction and PV across a number of combustion systems. Those good topologies are regularized simply by the virtue of connecting the encoding and decoding tasks in one optimization loop. During neural network training, the parameterization slowly adjusts to represent the QOIs uniquely and with smooth gradients. We also find that sometimes more than one good candidate for a PV is possible. And we test this by allowing all species to enter the PV definition versus not allowing pure stream components, so O2, NH3, and H2, to enter PV definition. And notice that these two topologies look differently, but they're both unique and represent the PV source term well. And by the way, in this work, we extensively use our earlier quantitative tools to assess the quality of those parameterizations. And if you're interested, you can check these two papers that provide those quantitative measures, which you can use in all sorts of research problems. I mentioned that the power of our approach lies in adapting the reduced model. In this work, we show some examples of this. So for instance, we test how does the parameterization topology change if we add one extra decoder output that is a particular species that we'd like to pay attention to. If that species is NO, this is the topology that we get. If it's N2O, we get this. If it's NO2, we get this. And if it's NH2, we get this. And you can see that there are some differences in how the parameterization topology adapts to also represent that one extra species. And most importantly, we seem to spread out regions where gradient in that species is highest. For example, we get this bulging out topology when targeting NO precisely in the region where NO is varying. And finally, we link our a priori assessments of parameterization with the success of a numerical simulation of zero-dimensional reactors. And here I'm showing the profiles of important thermochemical variables in a full order model. That is, if we solved all transport equations for temperature and all mass fractions. And these are reconstructed profiles from a reduced simulation that used our optimized PV definition. You can see that they match quite well. We also show a couple of failure examples. For instance, if we took one of the ad hoc PV definitions for this combustion dataset, we get these profiles. And the reason for a much poorer performance in this case is that the parameterization topology exhibits significant non-uniqueness along a large part of the thermochemical state space. You'll find the link to our paper in the video description. And if you're interested in reproducing our results or our figures and using our encoders, decoders for your combustion problems, you'll find our code in this GitHub repository.